But we can replace, if you like, this notion of the limits by a concept of a continuity, which is going to be easier to handle for future. Okay, if you go to the higher dimensions or go to the space that it's going to be quite arbitrary, then the notion of the limits is not going to be working. So that's why we replace it by the notion of the continuity. But calculus was done without continuity for 50 years. And then they come back and they add the notion of the continuity. It was added by great German mathematician. His name is Karl Weierstrass. Okay, so there you are. Let's see what's going to be. This is section 1.1.4. You are going to have 2 questions from the continuity on the quiz. So 6 questions, 4 on the limits, and 2 questions on continuity. So what's going to be continuous function or continuity of? Okay, what is continuity of functions? Continuity of functions. Remember, when we talk about the limit of the function, we estimate. Okay, we estimate the value of the function around a given number. That number was a. So that's estimation of the value of the function. But if you directly substitute a into the function and you find f of a is the exact, okay, it's going to be the exact value of the function at a. So the limit is an estimation of the value of the function at the point a, but f of a is the exact value. If these two happen to be equal to each other, in that case, we say the function is continuous at x equal to the a. Okay, so the continuity, you must match the limit of the function and the value of the function together. So a function is continuous if the limit of the function at that number we call it a, is the same as f of a. Okay, so that's the definition of the continuity. So we give a definition first. So there you are, a function. Okay, a function f is going to be continuous, is going to be continuous at a number. Number a is simply if the limit of the function, limit of f of x, when x goes to a, you see this is an estimate. This must be equal to the f of a when you directly substitute. So if this is going to be the case, we say the function is continuous at the number a. Now, if you can do this one for all values in the domain of your function, then you can say that the function is continuous in the entire domain or on the entire domain of the function. Okay, so if we can do this one forever, if f is going to be continuous, f is going to be continuous for all values of the variable x of x in the entire domain, in its domain, okay, domain D, domain of the function, then we say the function is continuous on its domain. Then f is set to be, okay, set to be continuous, set to be continuous on the domain D. Okay, so the first one would be continuity at one point. The second one would be continuity in the entire domain of the function. Now, from geometry point of view, when you have this condition, you see when the estimate and the exact value are going to be the same, the graph of the function at the point x equal to the a cannot have any hole, okay, cannot have any gap. So if the function is going to be continuous on its entire domain, if you graph it, you're not going to see any holes, okay, or you're not going to see any gap. The graph of the function is simply one piece, okay? So that's sometimes, the graph would be given to you and they ask you to determine the point of the continuity of the function. So you have to check to see if there is any hole or there is going to be any gap. So we're going to emphasize this one. So we say that in this case, so this means the case that it is going to be continuous. In this case, the graph of the function, okay, the graph y equal to the f of x, in this case has no gaps, if you like, or holes, if you like. It is going to be like, it's a one-piece graph. It is one piece graph, if you like. It's not going to be any hole. Okay, that would help us when we see the graph to guess first. Let's give you examples, just geometry first. So from geometry point of view, if you be given this graph, look at this one. If this is given to you, you see this graph. As you can see, as you move on, there's no breaking point, there's no gap. There's not going to be a separation of points. It's just one point. It's a one piece. You see, if I want to graph it, I just move on. I start with putting the pen, the pencil down, and then I can do it. So that would be a continuous graph. This is a continuous function. So this function, if you like, is continuous. So this function, a function, if it's given to you and they ask you where this function is continuous, you say the function is continuous everywhere. Is continuous, okay, everywhere, because it's a one piece. Okay, any question? Give you another one. But if this is going to be a graph of your function, look at this one. You get something like this one, but a little bit up here, okay? So you may get something else. You see, this graph is, there is a gap between the parts of the graph. In two parts, it's separated. So it's not a continuous function, okay, because there is a gap here. So this is going to be called a discontinuous function. So it is a discontinuous, okay, a discontinuous function. So that would be your job, not geometry, of course, algebra, to just prove for us or find out where the function is going to be continuous. Okay, any question? So if it's going to be continuous, you can easily graph it. You see, this is continuous. But if you want, in order to get your graph, if you graph a while and then come back and you want to repeat it, so it's a two pieces. So this is going to be discontinuous, okay? But this is going to be continuous. This is discontinuous, and this is going to be continuous. Okay, so that's of course geometry. Geometry won't prove everything, okay, or anything for us. So let's see how we're going to do it using the definition that we have over here. Your job is we give you the function and we ask you where this function is going to be continuous. And there's going to be easy method to do it, but let's give you some example first. Any question? So a function is continuous. You see, when we take the limit, we don't care about f of a. Remember, we say the function x is not equal to the a. But when you get the continuity, you do care about f of a. So that f of a must be equal to the limit of the function. So let's get some familiar example. We want to know where these functions are going to be continuous. And the best one is, that polynomials. We already talked about this direct substitution. So if, for example, if f of x is going to be equal to the x cubed minus 3x plus 1, you know that this is a polynomial. And we talk about it. If you want to find the limit of the polynomial, it's a direct substitution. So in case of the polynomials, all the polynomials are going to be continuous. So if this is going to be the case, then you know that f is a polynomial. F is a polynomial. Polynomial function, if you like, with the domain of the ordinary numbers, domain R. Okay, that's going to be the case. Now you know that, and note that if you pick any number A, you see if A is a number, you already done this one several times. If A is a number, so what you're going to have, you see the limit of f of x when x goes to A. This is x, okay? You know that you just direct substitute. So that give you what? That give you a cubed minus 3a plus 1, which is the same as f of a. And we've been using this one over and over so far. Okay, so as you can see, the limit of the function for the polynomials are going to be always the same as the values of the function. So this simply means this function is continuous. Okay, so f is continuous. F is going to be continuous everywhere. Continuous everywhere. Everywhere, okay, on R. We are going to make this one official and use it. So if this is given to you from now on the test for the rest of the course, if this function is given to you and they ask you where this function is continuous, this is how you answer it. You say f is a polynomial. And so it's continuous everywhere. Done. I'm going to write it down as a theorem in a minute to see how we are going to handling this type of problems. Any question? Now, it's a good place to mention is that you see in calculus or in mathematics, mostly we talk about two types of functions from now on. Mostly the interesting one are polynomials. So polynomials are the best type of function or the easiest type of function that we're going to have. Now you have the continuous function. As you can see, every polynomial is continuous. So you may wonder about the relationship between continuity and the polynomials. You see, calculus was done for 50 years without notion of the continuity. And they didn't have any difficulty because they work with the polynomials all the time. Weierstrass, Karl Weierstrass, you see, you will know his name. That is, you can search on internet and you see quite a lot about him, and we are going to talk about him again. Karl Weierstrass. I think that's the way we write it down. Weierstrass. That is Karl Weierstrass, German mathematician. He proved something quite interesting. He proved that he created, he just modified, extended the notion of the limits that we use today. And by that extension, he proved that every continuous function can be estimated by a polynomial. You see great theorems. Every continuous function, can be approximated, by a polynomial, That's a great result in mathematics. So that's why every course you take, they start with the polynomials. They emphasize polynomials, polynomials, polynomials. Why? Because we don't have anything else. If you have anything else, you see anything else means if you have a continuous function. That can be estimated by a polynomial. So if you are in physics, okay, in mathematics, if you want to prove something for the functions, they usually ask you to start with the polynomial. If you can prove your statement for polynomial, then they say, oh, by Weierstrass theorem, we can have it all for the continuous function as well. So that's a great result. And that's why the continuity notion was introduced by Carl Weierstrass. This result in mathematics, we call it the Weierstrass approximation theorem. If you check on internet, as soon as you put the Carl Weierstrass, they give you that theorem. That's a great theorem. If you are going to be a math major, you know, this can be proved, but you have to be a math major, and you know, you see it in your last year before graduation, and you may see it when you do a master program for the proof of this theorem. This is a very famous theorem. It was introduced by Carl Weierstrass, but later on it was extended by a great American mathematician. His name is Stone. So we have this result today is known as this one. Not bad to see this history. They call it Weierstrass. If you check on internet again, Weierstrass. Sorry, they call Stone Weierstrass. Stone. He was alive, you know, just a few years ago. I met him in some of these conferences. So Stone Weierstrass approximation theorem. Approximation theorem. It's a great result. It'll be between the continuity and so the proof of the Weierstrass is very classic. Stone extended a little bit, you know, extended a little bit. So today we call it a Stone-Weierstrass approximation theorem. So basically this means if you want to live in calculus, make sure you know everything about polynomials. As soon as your calculator will do it for you. See the way the calculator is operating, the calculator you can approximate every continuous function for you with the polynomials and give you the result right away. Okay, so that would be the first example, just a piece of history to know it. Any question? So we give it as a theorem, then you'll be safe with the polynomials. Your main question or job is when this function is not going to be a polynomial, especially when a piecewise defined function, okay? So the next example or the next group that you're going to have, okay, are you ready? This example is important, and this is the one type of the question that you're going to see. I'm going to list all of them for you in a minute. So pay attention to this type of the examples. So what we would like to do is, this is it, suppose. As we talk about it, the best type of example in calculus are going to be piecewise defined. Suppose we have this function, f of x equal to, you see it's equal to the x squared minus 1 on the top, x minus 1 down the bottom. This is where x is not equal to 1. Okay. And suppose this is equal to 2 when x is equal to 1. See, the partition point is 1. They ask you if this function is continuous at the partition point. So the question is that going to be is f continuous at x equal to 1. That's it. So you have to check the continuity. What you have to check? You have to check the limit of f of x equals to 1. And you have to check f of 1. If both of them happen to be equal to each other, the answer is yes. Otherwise, the answer is no. Okay? So the solution, you have to answer this one. Answer this, that the limit of f of x when x goes to 1, is it equal to f of 1? That's the question. Go and find it. Limit first. Limit of f of x when x goes to 1. Remember, it's a piecewise defining function. You have to decide which part are going to use. Remember, when x goes to 1, this means x is not equal to 1 because we estimate it. So when x is not equal to 1, this is your function. Okay, so I just remind you, this is just for your information. You talk to yourself, you say, oh, x goes to 1, so this means x is not equal to 1. So my function is the first part. Limit of x squared minus 1, x minus 1, x goes to 1. Now you have to find this limit. Direct substitution, if you put the 1, so that give 1 minus 1, 1 minus 1, that gives you 0, 0. Okay, what's the message for 0, 0? Message.
It's indeterminate form, so more work is needed.
Yes. So you know that there is a common factor. What is that common factor?
It's going to be x minus 1.
Excellent, x minus 1. So we go back and we do it. Yes, x minus 1 is a common factor. Just for your information, x minus 1 is a common. So be prepared for it. Common factor, just for reference. So this means more work is needed. Yes. So it's a limit of, and you can know, you can factor it right away at the beginning. So this is going to be x minus 1, x plus 1. Okay. This is going to be the case. So we have the x minus 1 here. X goes to 1. So we are going to divide by x minus 1. So the leftover would be the limit of x plus 1. Okay, x goes to 1. Now this is the direct substitution. That gives you 1 plus 1, which is equal to 2. So the limit of the function, limit of f of x, when x goes to 1 is equal to 2. That is the limit. Any question? So we find the left-hand side. Now the right-hand side, but it's going to be f of 2. Note that. Sorry, f of 1. What is f of 1? You go to the function. You want to see x equal to 1. As you can see, when x is equal to 1, the value of the function is given to is equal to 2. So f of 1 is equal to 2. That's it. So the value of the function, you see the limit of the function, limit of f of x, x goes to 1, is equal to the f of 1. These two numbers are the same. If they are going to be different, the function is not continuous, but the value of the function and estimation are the same. So f is continuous. It's going to be continuous. Okay, at x equal to 1. So the answer is yes. It is continuous. Okay, so you have this type of problem in your assignment, so you are able to do it. Any question? So that give an idea. Now we are going to make it official. Remember, this is just it's like working with the limits all the time. So what you can do is we can summarize the previous theorem that we did have. Remember that theorem, computing theorem. Go back to the computing theorem, and whenever you use the limit, change it to the continuity. Then you get the similar result over here that give you a tool to be able to check the continuity again directly. For example, we did have, remember, the sum of the limit of the sum of two functions are going to be sum of the limits. So if you change it to the language of the continuity, this means if two functions, f and g, are going to be continuous, then the sum function f plus g is continuous, f minus g is continuous, f times g is continuous, and f divided by g. So we are going to use that one, give you this theorem. So you are going to use this theorem to answer the continuity question for us, okay? There is only one place that you can't use it, and that's a piecewise defining function. Otherwise, we are ready for it, okay? So That is going to be a kind of computing theorem for the continuity. So use this to check the answer for where the function is continuous. There you are. I just repeat those parts that we did for the computing one. The first part, operation with the continuity. If two functions are continuous, sum function f plus g, difference f minus g, the product f times g, the quotient f over g, they are all continuous. So if the functions, f and g, okay, are going to be continuous. If they are continuous, two functions going to be continuous at a number a, okay, at a number a, then the functions, their combinations. Okay, the functions, what type of function? F plus g, f plus g, f minus g, the difference, f times g, the product, f divided by g, the quotient. Of course, this last one with the condition that the g is not equal to the 0. Okay, so if these functions, two functions are going to be continuous, so these are going to be all continuous, are also continuous, are also continuous. Okay, going to be continuous again at x equal to a. Okay, so this means as we talk about it, the sum, the difference, the product and the quotient of the continuous functions are also continuous. That's the case one. Any question? The proof is very easy. You see, because you know that the limit of f plus g is what? Is limit f plus limit g. But limit f would be f of a. Limit g would be g of a because of the continuity. So that gives you f of a plus g of a. So the sum is continuous. The difference the same, the product, etc. The key one is this one. Polynomials. Polynomials are continuous forever. If p of x, that will help you quite a lot again. You can do all the problem, solve all the problem using this one only. If p of x is a polynomial, it's going to be a polynomial, okay, polynomial function. If these are, it's going to be a polynomial function, then simply p of x is continuous. It's going to be continuous. It's continuous everywhere. Everywhere. Okay, everywhere means for all real numbers. So if a polynomial given to you, nothing to worry about. Quickly you can say it's continuous. You know that because the limits, when you want to find the limit of the polynomial function, remember you do the direct substitution. So that's why it's continuous right away. Okay, any question? We need one for the piecewise defined function. For the, you remember for the piecewise defined, define the right limit and the left limit. If they were the same, then we have the limits. But if they were not, okay, the limit does not exist. So it's going to be the same thing over here. But the right and the left limit in that case, we are going to call it the right continuity and the left continuity. Okay, it's the same thing. So we use this one for the piecewise defined function. And that is going to be the case. F is continuous. F is going to be continuous. Okay, at x equal to the a, if and only if. Right limit, left limit is the same, means if and only if f is continuous. F is going to be continuous. at x equal to the a, both from the left and from the right. From the left and from the right. From the right at x equal to the a. So again, we check the right and the left limits, okay? If the right limit is equal to the f of a, in that case, it's going to be continuous, okay, from the right. If the left limit happen to be, it's going to be continuous from the left. But, you know, if they are, you get two different numbers. So this means if the right limit and the left limits are not going to be the same, so in that case, your function is going to be discontinuous. So we use this one, okay, quite a lot. So this simply means, you know, the reason is this one. Limit of f of x, you see x goes to a is equal to the f of a, even only if the limit of f of x goes to a negative is equal to the f of a, that's the left limit, and the limit of f of x goes to a positive is also equal to the f of a. So again, it's nothing new. Okay, we did have it for the, we did have this one for the limits, so we just change it to the language of the continuity. Okay, that's a number 3. Number 4, all the popular functions, trigonometric functions especially, they are continuous. So we make a note over here and we use it without any proof when we get to it during the during the examples in this course. Okay, so we just make a record that all, you know that, you know, if you look at the graphs, you will see there are part 1 pieces. So all the 6 famous trig functions, trigonometric metric functions, I mean sine x, cosine x, you know, the tan x, and those, you know, secant, cosecant, cotan, they're all continuous, are going to be continuous on their domains, on their natural, you know, natural domains, if you like. So that's it. This is all the result that we need to be able to take care of the continuity of the functions. So the main one is this one again, as you did it for the limits, polynomials. Polynomials are continuous forever. So then you may have a combination of continuous one, then you take care of it right away. Okay, any question? We don't need anything else for the continuity, and we're not going to talk about anything else. So your main job is that 2 questions. 2 groups of functions would be given to you, and you are going to determine where those functions are going to be continuous for us, okay? So as soon as I write it down, you find out that we already done this one when we review for this course, okay? So pay attention to this group of the examples, and both of them would be given to you on this quiz and on your first test, and we're done. Any question? To give you an example to get the idea of what I'm talking about. This is the first group. So this is how we're going to ask you the question of the continuity. We would like you to find the interval example. Find the interval. Find. You have to use the interval notation. Find the interval. Okay, find the interval where function is, where the given function, where the function is continuous. The function is continuous. That's it. You can use those theorems that I talked about, remember. Okay, are you ready? There are kind of 6 types of functions. The first one, f of x equal to x to the 5th minus 2x plus 1. We want to know where this function is going to be continuous. Remember, we want to use that theorem. So you start with the checking to see what type of function is this one. Any suggestion?
Polynomial.
Excellent, that's it, polynomials. And we know that the polynomials are continuous forever. Done. Okay, it's like finding the domain of the function. It's the same thing over here. So it's a polynomial. And you know that in the case of the polynomials, the limit and the direct substitution are the same. And when the limit and the direct substitution are the same, the function is continuous. We can do it all the time. So this is how you simply answer this question. Solution. You simply say that f is a polynomial. F is a polynomial. Or a polynomial function, just a polynomial would be fine. And we know that it's continuous. And so is continuous. Is continuous everywhere. Or it's continuous on what? On D. You can say D equal to the R. They ask for the interval. So it's going to be continuous on negative infinity and positive infinity. Okay, we also accept when you write D equal to the R. That's it. Okay, so you identify that it's a polynomial. You don't have to prove it for us, you see, because we know that the limit of these functions can be found by using the direct substitution. And we have the theorem here. You see that the purple one, if p of x is a polynomial, it's continuous forever. So you identify that it is a polynomial, so it's continuous forever, and then we're done. That's the type one. Any question? So that the important part is to check what type of function do you have. So ready for the next one? The next group, of course, a rational function. G of x equal to x minus 1 over x squared minus 4. It's a rational function because of the x here. You know that it's a quotient of two functions. The top, x minus 1, polynomial, continuous. The bottom one, continuous, polynomials. So the top continuous, the bottom continuous. So the quotient of two continuous function is continuous. But what is the catch? The catch is going to be it's continuous everywhere except when the denominator is 0, the domain of these functions. Okay, so we have no difficulty for the continuity except when the denominator is 0. So this is how we're going to answer this one. As we talked about it before, you may factor the denominator to see where you have to exclude those numbers. So as you can see, the domain of your function is going to be what? As we talked about it before, that's a negative infinity to positive infinity. You have to exclude two numbers, -2 and the +2, because the denominator would be 0 at 2 and, okay, at -2 and 2. So the function is going to be continuous on this interval. It's 3 portion, 1, 2, 3. So the G is going to be continuous. You see, that's it. G is continuous. G is continuous on this interval, just from -infinity. It's a domain of the function, if you like. Okay, -infinity up to the -2, union with -2 and +2, union with 2 and positive infinity. So that would be, this is a just the domain of the function. You see, you know that this is the domain of your function, which is a negative infinity, -2, union with -2 and 2, and the union with 2 and positive infinity. So the only difficulty for this function is when the denominator is equal to the 0. So it's like the domain as you did it before. Any question? So we're just using that fact. You don't have to give us any details. Okay, when is not considered to be continuous? It's not going to be continuous at, you see, at 2 and -2. You see, it's continuous everywhere except at -2 and 2. So this function is discontinuous. It's going to be discontinuous at x equal to the 2. Okay, you know that if you graph it, it's going to be two pieces. It's going to be pieces at the -2 and 2 because of the asymptote. Okay, any question? So when it's a rational function, just exclude the zeros of the denominator to get where your function is going to be continuous. That's a type 2. For the rational function, you may get another one. That's why I reviewed this one, remember, at the beginning. How about this one? H of x equal to, is a rational function again. But denominator is this, x squared plus, let's say x squared plus 5. Is a rational function again. Can you tell us where this function is continuous? Any suggestion?
Everywhere.
Very good. Everywhere. Yes, excellent. You see, the top is continuous, the bottom is continuous. So the only you have to worry about if the denominator can be 0. But this is x squared plus 5. You know that x squared plus 5, you cannot factor it. You can factor x squared minus 5. You see, x squared minus 5 would be x minus radical 5 times x plus radical 5. So denominator is never 0 because it's x squared plus. So x squared is positive. So you never be able to make denominator equal to 0. So it's all number line. Okay, so that's you will see this one from time to time. So the solution is going to be, so that you just note that, that's it, note that x squared plus 5 is, okay, you can say that it's not factorable if you like, not factorable. And so it's never 0. Okay, so that's going to be the case. So H is continuous everywhere. H is continuous. Okay, everywhere on the domain, negative infinity and positive infinity. And then you're done. Okay, so this is one of those that, you know, from time to time you will see it. So just make sure you be able to identify it. Any question? I'm going to modify this one a little bit. This is the one that some people, they miss it on the test. Let's see what's special about this. It's going to be x minus 5 over x squared minus 25. See, very similar to the previous one. We want to check where this is going to be continuous. Of course, we have x squared minus 25. We have to factor it first. Okay, so let's do the factoring. So the solution is going to be, so this is going to be f of x equal to, we have the x minus 5 on the top, x minus 5 times x plus 5. Okay, any suggestion where this is going to be continuous? Again, you know that the top is continuous, the bottom is continuous. So you have only to worry about for the values of x, which makes the denominator equal to 0. For what value of x, or the values of x, the denominator would be 0?
5.
5 and
-5.
that's it, 5 and -5. So there are two places that you make it 0, so you have to exclude it. You see, the reason that I give you this one is you didn't make a mistake. You see, that's a negative infinity, and that's a positive infinity. The thing is, you are not going to simplify that this part. When I gave this one on the test, some people, they simplify it, then they continue. No, you keep it as is. You see, because this is a -5 now, and that's a +5. You see, the denominator is 0 at 2 places. So the function is not going to be continuous at -5 and 2 and 5. So f is continuous on this interval. F is continuous. We like interval notation. It's going to be continuous everywhere except those -5 and 5. So we write it down as -infinity up to the -5, union with -5 and 5, union with 5 and +infinity. So that would be the domain of the continuity. Okay, so don't simplify. Don't simplify it because they ask for the continuity. It's not algebra. Okay, so if you simplify it, you miss one of those points. But if you graph it, you will see 2 holes. Okay, 2 holes on this graph, one at -5 and one at 5, or just would be separated one. So when you're dealing with a rational function, be careful. You may have this one, x² plus something. This is not factorable, so nothing to worry about. So it's all number line. Okay, it's continuous. But when it is factorable, check the factors, take out the numbers that you're going to exclude, then determine the domain of the continuity. Any question? One more group. Remember, radical functions. You already got the experience of the radical function. We are going to consider them when the index of the radical happen to be odd, or the index of the radical happen to be even. So that would be our number 5. Again, that's a popular function. We're going to use it. So what's going to be number 5? Let's start with this one. A g of x equal to is equal to the 5th root of the 3x² minus 5x plus 1. Remember, like the thing that you did for the domain of these functions. Index of the radical is 5, odd numbers. Remember, when the index is odd, forget about radical, leave it. Look at this function. What type of function is the one inside the radical? The function 3x minus 5x.
Polynomial.
Polynomials. And you know that the polynomials are continuous everywhere with that. Okay, so when the x is odd, we are not going to worry about. You have to worry about when the index is even. So simply, this is how we're going to answer this one. Solution. You're going to mention that the index 5 is odd. That's it. When 5 is odd, you look inside. Inside is a polynomial, it's continuous everywhere. You can say that, and so G is continuous. Everywhere means continuous on R, or the domain. They ask for the interval, so it's a -infinity and +infinity. And you're done. Okay, so when the index is odd, because we can find the odd root of any number. And the inside is a nice polynomial, and the polynomials are continuous. Okay, any question? Now, the challenging one for the radicals, of course, is where the index is even. So let's give you this one, g of x equal to the 4th root of x² minus 3 now. So that's it. What is the challenge now? The challenge is the index is 4. 4 is even. Remember, when it's even, x² minus 3 cannot be negative. So you have to force it to be greater than or equal to the 0, and find the domain. That domain give you continuity because you know that x squared minus 3 is a polynomial. X squared minus 3 is a polynomial, it's continuous everywhere. But the question is, can you take everything outside of the radical? No. We can take it out if this x squared minus 3 is not a negative number. So this is how you're going to describe your solution for this group. You go with the index first, index 4 is even. So this means your function is continuous because of the polynomial. G is continuous, but only when you guarantee that the x squared minus 3 is greater than or equal to 0. You see? Because you need this guarantee to make sure that you are able to take these numbers out. If you put x equal to 0, that gives -3. The fourth root of -3 doesn't make sense. It's not a real number. Okay, so you have to solve this inequality. We talk about it, we express two different methods. The short one is just the absolute value version. So you go on, x squared greater than or equal to 3. You take the square root. Okay, and we talk about this one. What's radical x squared?
The absolute value of x.
Excellent, make sure to remember it. And the method that we talk about to solve this is it, get the number line. It's a negative infinity to positive infinity, absolute value or distance from home. This is home, 0. It's a radical 3 on the right, and the negative radical 3 on the left. It's greater than, you see x greater than. When it's a greater than, you are not going to be inside. You go outside, this is greater than. Looking into the mirror, and this is greater than. So your function is going to be continuous in these two portions only. Okay, so G is continuous. It's going to be continuous in its domain. Continuous, okay, on the domain, which is, you start from negative infinity, you go to the negative radical 3, of course, bracket, because it's not a rational function. Union with, then you start with the radical 3, and you go on forever. So that would be where the function is going to be continuous. Any question? So yeah, we get all the possibilities for this group of functions, and the radical functions, polynomials, rational. We arrange it so that you will see all of them on your quiz to practice it. But the challenging one is this, the last one, the 5 and the 6. Okay. For the rational function, you have to exclude the zeros of the denominator. For the radical function, you got to be careful when the index is even. Otherwise, for the odd index, it's nicely done. Okay, to get this true. Why x absolute? Absolute, because you see, we talk about the radical x squared. You see the radical x squared. You cannot say that this is equal to the x, because the outside must be positive number all the time. So if you say this one, if I put x equal to -5, you see, then you'll be in trouble when you're removing the squared. Okay, when you're removing the squares, you guarantee it always with the absolute value. Okay, we use this one in several other places during this course. Be careful. Okay, any question? No, this is the first group. The second group, or the second example, is the piecewise defined function. Okay, the one that we did. So we need number 7 to finish it. And this is it, the two questions would be given to. One of them would involve this. We put all these cases together as 2 questions, probably 2 parts. So we may have to consider 4 different functions to check for us. But one of them would be piecewise defined. Okay, so I need more room. So I go to the next page. And this one is different. And this is, in fact, the one that we are going to use in several places for future. So pay attention, but you will see it on your quiz one, and of course, then test one. This is the function. It's going to be a piecewise defined. The function is defined by, we have the x squared minus 3x. Okay, this is where x is less than 2. And we have 7x minus 1. Okay, when x is greater than or equal to 2. This is the function, and they ask you where this function is going to be continuous. You see, from now on, in calculus, this is how you handle this type of problems, piecewise defined function. Anytime they give a piecewise defined function, your challenge is going to be around the 2 only. Because if you go a little bit less than 2, your function would be x squared minus 2x. A little bit more, 7x. So you have 2 different cases. For the other part, you have nothing to worry about. So if you forget about the 2, you see this function x squared minus 3x is a polynomial, is continuous. 7x minus 1 is a polynomial, is continuous. So we have nothing to worry about when x is not equal to 2. So we can start with this solution. It's true for everything else in this course that we're going to have. Okay, so you start with the fact that note that f is continuous. F is continuous when x is not equal to 2. Okay, when it says not equal to 2, this means if it's less than 2, x squared minus 3x, nice polynomial continuous. If x is greater than 2, 7x minus 1. So the difficulty is 2. You see this graph is 2 pieces. It's a 2 pieces, the piece 1 and the piece 2. By themselves, they are continuous function. But when they get to this partition point, you have 2 different cases. At this partition point, the graph may meet each other. So they are going to be continuous again at 2. Your function is continuous forever, or they may not. If they stay separated, so this means there's going to be a hole at 2. So this means the function is continuous everywhere except at 2. So your job is check the continuity at 2. Since it's a piecewise defined function, you have to check the right limit and the left limits all the time. If the right and the left are the same, so this means they are going to be connected to each other. So the function is also continuous at 2, and the function would be continuous forever. If the right and the left limit at 2 are not the same, so this means the function is not continuous at 2. So the function would be continuous everywhere except at 2. Okay, so your main job is checking the continuity at x equal to 2 by looking at the one-sided limit, right and the left limit at 2. It's the same for the differentiability. Later on that we are going to talk about it, okay? And if you take application in science, as I talked about it before, all the functions are in science are going to be of this group. So that's why we need this. Okay, so this is how you're going to, you do it right away. I just explained here. So what you have to do is this, check the partition point, check the continuity, check the continuity of function of f at partition point, x equal to, okay, at x equal to 2. Now we're going to check it by finding right and the left limits. I call it one-sided limit. One-sided limits. One-sided limits of f at x equal to 2, the partition point. When you check it, there are 2 possibilities. If the limit does exist, this function is continuous forever. If it doesn't, the function is continuous everywhere except at 2. There is a hole here. Okay, any question? So check right, left limits. So I'm checking the left first, limit of f of x. X goes to what? 2 negative. We already talked about it. X goes to 2 negative means x is less than 2. The function to be used is the first one. So it's going to be equal to the limit of x squared minus 3x. X goes to 2 negative. Now you substitute 2 because that negative top one is just a direction. So it's a 2 squared minus 3 times 2 is a 4 minus 6, which is equal to the negative 2. So the left limit is negative 2. Any question? Check the right. Limit of f of x. X goes to 2 positive. X goes to positive means x is greater than 2. When x is greater than 2, you have 7x minus 1. So that gives the limit of 7x minus 1. X goes to 2 positive. Substitute 2 for x. 7 times 2 minus 1. 14 minus 1. 13. You see, we get two different numbers. So negative 2 is not equal to 13. So this means at this point, the graph would have a hole. You see, this means this is a negative infinity and positive infinity. At 2, you have a hole here. So the function is not continuous at 2. Okay, so f is not continuous. Not continuous. Okay, at x equal to 2. And the conclusion is going to be, the conclusion, f is continuous. F is continuous. Okay, on this interval. The interval is a negative infinity up to the 2, open, union with 2 and positive infinity. That's it. You see, the domain of the function is all real numbers, but this function is not continuous at 2. And this is the way we do it. If these two numbers happen to be the same, and you got the equality sign here, this means this function is going to be continuous, okay, continuous forever. So check the part, there are two cases. If they are different, this is it, it's continuous everywhere except at 2. If they are the same, it's continuous between negative infinity and positive infinity. And there are no other possibilities for this group of functions. That's it. We are not going to cover anything else from the continuous functions. We don't need it to get this. Okay, of course, you know, if you're going to be math major, you may see more, but from now on, this is the best type of function that we can have other than the polynomials. So in most of the cases that we are going to have, we are going to use the continuous function. Okay, so a function is continuous. From the geometry point of view, if the graph of the function would be only one piece, okay, no holes, no separation, okay, no gaps. But if there is going to be a gap at that one point, in that case, your function is not going to be continuous at that, okay, that point. So we are ready to go to the practice quiz. I think I give you a break now. So you can have your 10-minute breaks. We come back, we do the practice quiz. Number 1 is the one that I posted on the canvas, okay? So I give you the solution. We get time to give you a solution of all of them or most of them, and then you'll be able to do the quiz for us. So we are done with chapter 1. Chapter 1, and your quiz will cover these sections, 6 questions, and I'm going to identify it when I go with that. Okay, any question? So have a 10 minutes and check the canvas for that practice one that we have to make sure they know which part I'm going to talk about it. Okay, see you in 10 minutes. Okay, so we are going to go on that practice quiz. Give you the topics that are going to be important, and we could give into 6 questions. Okay, 6 topics, 4 on the limits and 2 on the continuity. Okay, there you are. This is the one that I already posted for you. Okay, so you just go with the numbers over there. So this is it. And you keep these solutions for your next test as well, because we are not going to repeat this, review these topics again, but we give you this 5 question again on your test 1. Okay, the number 1, we are interested in the piecewise defined function as we did it now. So 1 question would be given to you, and we ask you the following, find the right left limits, the behavior of the function at that partition point, in fact. So this is going to be the case 1 that we have. Number 1, so this is your function. Okay, the function is given to you, f of x equal to piecewise defined 5 minus 2x when x is less than 3, and then 1 plus 3x when x is greater than or equal to 3. Okay, and they ask for the behavior of the function at 3. For part 1, you've been asked what is the limit of the function. Okay, limit of the function when x goes to 3 negative. So that's the first part. So the way you do it, this is it, x goes to 3 negative. We talk about it, this means estimating the x from the left at 3 from the left. So x goes to 3 negative means x is less than 3. So less than 3, the function to be used is this one. So you bring your function, direct substitution, give you the result. Okay, so this is how you would do it. The limit of f of x goes to 3 negative. Just this is for your information. X goes to 3 negative means x is less than 3. So the function to be used is the first part. 5 minus 2x, and this is just a polynomial. Directly substitute 3 for x, 5 minus 2 times 3. So that gives a 5 minus 6, which is equal to the negative 1, and you're done. That is the left limits. Any question? So read it carefully. Sometimes they switch, they go with the x goes to 3 positive first. But make sure that you do you do the proper one. That's a part 1. Part 2, they ask for the limit of f of x goes to 3 positive. Again, it's a limit of f of x goes to 3 positive. You remind yourself that this means x is greater than 3. You don't have to write it down on the test. But x greater than 3, the function is 1 plus 3x. So we are going to take the limit of 1 plus 3x. Okay, when x goes to 3 positive. Now from now on, direct substitution, 1 plus 3 times 3 is going to be 1 plus 9 equal to 10. Okay, so the left and the right limits are 2 different numbers. And when there are 2 different numbers, we know that in that case, the limit of the function does not exist. If these 2 happen to be the same, so that same number would be the limit of the function. And this is what you're going to do for the part, part C. Part C, you've been asked what is the limit of f of x goes to 3. So your answer would be, you say that the limit of f of x goes to 3 negative is not equal to the limit of f of x goes to 3 positive. So that would imply that the limit does not exist. Limit of f of x goes to 3 does not exist, and we accept it. Any question? You have to give us a reason. You write this one, or you say that -1 is not equal to the 10. You see the other way we write it down on the test, we accept it. You say that the -1 is not equal to the 10. So this means the limit of f of x goes to 3 does not exist. Give us a reason. Don't just say does not exist. We don't accept it. Any question? So the other possibility is these two happen to be the same number. So that same number is going to be your limit. Okay. That's a part C. Part D, they ask for the actual value, the exact value. Okay, what is f of 3? F of 3. You go to see if you have this option of x equal to 3. You see, x equal to 3 is here. So we use the second one to find f of 3. If this equality sign was missing, f of 3 is undefined. Okay, in this case, we can do it. So in order to find f of 3, the second option, 1 plus 3 times 3 is a 1 plus 9 equal to 10, the final answer. Okay, so this is how we handle this first problem. It's a very important case. We like this one because, if you want to continue calculus, these are the type of function that you're going to have. And when we get to differentiability, there are a group of these functions that we have to, we have to consider it. And this is the way we are going to do it. If the equality sign was not given, in that case, you say f of 3 is undefined. Okay, it does not exist or undefined, this part. So this problem would have two other possibilities. The possibility that the equality was missing. So in that case, you say f of 3 is undefined or does not exist. And the case that you may get these two happen to be the same. If these two happen to be the same number, so that same number would be the limit of the function. Okay, so the case that you're going to have are going to be one of those possibilities. Okay, that's the type 1. Any question? Now, the type 2 problem related to this one is kind of the converse of these ideas. Remember, a function would be given to, because we know that sometimes it's happened to be the same, sometimes not. But they may give you something with the parameter m. You want to force the function so that always you get the answer, positive answer. That's the case 2. Any question? So write nicely, okay, when you want to give us the result. So that was the number 1. Number 2, the topic number 2 related to this one is the converse problem. Number 2. You have 2 cases over here. They are very much the same. Let's try one of them. Part 1. What is the part 1? The part 1 is you have a function f of x is equal to the negative x plus 1. Okay, negative x plus 1 when x is less than or equal to 3. Okay, and is equal to the mx minus 8 when x is greater than 3. You see there is an unknown here, m. So what we would like to do is we would like to find the value of the m for which this right and the left limits are the same, or for which the limit of the function does exist. Okay, so that's a problem. They ask you to find the constant. Okay, that's a problem, the constant m, okay, such that the limit at 3 does exist. You know that the limit may exist or may not. See, that is what they're asking you. Okay, so what you have to do is, you know that the limit does exist if the right and the left limit are the same. So you find the right and the left limits, you let them to be equal, the same, because you would like it. Then you find the m. So in order to find the m, you need an equation. So that's the equation that you have. Okay, so this is going to be the solution. This is the one that I told you that you have to be careful to write it down correctly. Okay, this is it. You say that, oh, since limit of f of x, or you want this one to be existed. Okay, since the limit of f of x goes to 3 exists, then it follows that, it's just for information, it follows that the right and the left limit, you see the limit of f of x goes to 3 negative is the same as the limit of f of x goes to the 3 positive. Okay, so this is your wish. You want to find the m so that these two happen to be the same. So that's it. Go and find it. Bring the limits from the left and the right and the left limits. Let them to be equal to each other. That give you an equation. Solve it for m. Okay, so that's going to be your job. Just do it step by step. Step 1, just go limit of f of x. Okay, x goes to 3 negative. Again, now you know that 3 negative means x is less than 3. The function to be used is the first part. So that give it a limit of negative x plus 1. X goes to 3 negative. That negative on the top is the direction. So we took care of the direction. Now direct substitution, you put x equal to 3. So that give you -2 for the left limit. Any question? Do the same thing to the other side. So what's going to be the limit of f of x? X goes to 3 positive. The other side. X goes to 3 positive means x is greater than 3. So you have to use the second part. So that gives you the limit of mx minus 8 when x goes to 3 positive. Substitute 3 for x carefully. So that gives you m times 3 minus 8. It's a 3m minus 8. Okay, so the left limit -2, the right limit 3m minus 8. Let them to be equal to each other. Okay, that's it. Let them to be equal to each other. So that gives us a 3m minus 8 equal to the -2. Solve for m. Okay, so it's going to be 3m equal to the -2 plus 6 plus 8, which is going to be equal to the 6. So m would be, that's it, 6/3, which is equal to 2. So m must be 2 in order to be able to get to guarantee that the right and the left limits are going to be, okay, right and the left limit happen to be the same to get these numbers. Okay, any question? So this is the way you do it. I talk about it when we give you the lecture. Some other thing that the people they do it, and this is the order of the proof. Okay, I talk about the fact that some people they let the first part and the second part to be equal to each other. Then they substitute, which is not true. The limits must be the same. You see, the limits must be the same. The limits must be the same. You just substitute to get the numbers right away. Okay, so that's part 1. Part 2 is the same. It's much easier, but you see, in this case, they say the limit does exist. Sometimes they give you the fact that the right and the left is equal to each other. It's the same thing. Just find it, let them do equal to each other. Okay. So if we get time, I come back, I do the part B2, but it's the same thing. Any question? So that's the first topic. The topic is what? Piecewise defined function, right, left limits bounded, and the converse problem. That is the case 1 or the type 1 for the quiz. Type 2. Type 2, finding the limits. We call it special limits. Special limits are going to be the case that you get 0, 0. We get the 0, 0, and we have 3 different cases. And we give you all the 3 on this, okay, on this quiz. And you get quite a lot in this number 3. And I give you 3 of these. Okay, number 3. Special limits. So a special limits is the case that in determinant form, See, 0, 0. Remember, this is the one that when we get the 0, 0, we say, oh, there is a common factor. You have to find that common factor and then eliminate it. And we have those three cases with the polynomials, radical functions, okay, and the complex fraction types. So be prepared for it. One from each. There you are. So we want to evaluate each limit. That's number 3. I give you one from each. You have more to practice over here. Evaluate each limit. Case 1. Part 1, and this is the first one. The first one, you want to find the limit of x minus 3, x squared minus 8x plus 15. X goes to 3. That's a case 1. Okay, directly you substitute to confirm that you get a 0, 0. Because sometimes you may substitute and you get the actual result. Okay, so solution, I check it. 3 minus 3, 3 squared minus 8 times 3 plus 5. 3 minus 3 would be 0 on the top. Down the bottom, 3 squared 9 minus 24. Okay, minus 24 and the plus, I made a mistake here. This is 15. This is 15. Okay, that's going to be 15. 15. So that's plus 15. So now that's give you 0. Okay, that's going to be 0, 0. So we confirm that we get the 0, 0. As soon as we get the 0, 0, we talk about it. There is a message. What's the message for this one? Any suggestion?
There's a common factor,
Yes. And what is that common factor?
x minus 3.
X minus 3. That's it. You see, x goes to 3. Your common factor is x minus 3. So you have to go back, factor it, eliminate that factor, and come back again. Okay, so that's good for you to know it. You say x goes to 3, x minus 3. If x goes to negative 3, x plus 3. So the message is, you don't have to write it down for the solution, but it's good for yourself. Okay, x minus 3 is a common factor. Common factor. So go and factor it. On the top, you already got the x minus 3, so you have to factor the bottom one. So, or, you can start right away. We don't mind if you eliminate those details. It's nice to check. So there you are. The top one, it's already got x minus 3. The bottom one, you factor it. You already got one factor. You see, one factor is x minus 3. So quickly you find the other one. It's x squared, so we go with the x only. It's positive 15, so it's a negative 3. Negative 3 times what would be positive 15? Negative 3 times a negative 5 would be positive 15. Okay, so that would be helpful. So, and the x goes to 3. So eliminate the common factor. You see, you divide. When you divide, the leftover on the top is 1. So that gives you the limit of 1 on the top, x minus 5 down the bottom, and when x goes to 3. Now this is the time that you substitute to get your result. So it's going to be 1 over 3 minus 5, which is going to be a negative 2. Okay, so it's going to be 1 over negative 2, but the final answer would be negative 1/2. So it's equal to the negative 1/2, the final answer. Okay, you don't have to repeat it, but I repeat it. So x minus 3, x squared minus 8x plus 15. X goes to 3, happen to be equal to the negative 1/2, and we are done. Any question? At this level, this is the only solution or the only method that we're going to use in order to find these limits, okay? You cannot use any other method. You cannot use derivative. At the end of the course, we have another method, but you cannot use it now. Okay, so as soon as we get the 0, 0, there is a common factor. Since x goes to 3, so the common factor is x minus 3. So we got the x minus 3 on the top, we created on the bottom, eliminate it, and then you get the numbers. Okay, any question? That is type 1 when we get the 0, 0. So what's going to be the type 2? That's a part 1 that we're going to have. The type 2 is the one involving the absolute, it's going to be more, but I just go with the one that you have on this practice one. I explain everything. You see part B. Part B, they ask you this limit, the limit of absolute value of x over x. X goes to 0 negative. 0 negative. You see, remember we talked about for the absolute value, you have to take care of the absolute value first. You have to drop it. But you have to see what type of numbers do you have inside. Is it positive or is it negative? We check this one, x goes to 0 negative. X goes to 0 negative, what does it mean? So the solution. You see x goes to 0 negative for your information. That would imply that x is less than 0. Less than 0 means x is the negative numbers. X is less than 0, so that would imply that the absolute value of x, remember, is the opposite of the x, negative x. If x goes to 0 positive, then x would be positive. So the absolute value of x would be positive x. So go back, substitute, take the limits. So it's a limit of absolute value of x over x. X goes to 0 negative. So you change it to the limit of, the top would be a negative x, and this is going to be x. X goes to 0 negative. You have the common factor, which is x. So you simplify it. On the top, we get negative 1 over 1, which is going to be negative 1. So the limit is the limit of the absolute value of x over x. X goes to 0 negative is equal to the negative 1, and you're done. Any question? So when you have the absolute value, you have to drop the absolute value first. Otherwise, you can't do anything about it.
You have a quick question.
Yes.
Are you saying the absolute value of a positive number is the negative of it?
No.
Or specifically with just this scenario because you're coming
No,
from,
no,
from the left?
because x is negative, you see? Because x is negative. You see, x is negative 5. So what's
X is negative because it's approaching from the left?
excellent? Yes.
Okay.
Yes. So what is the answer to this one? No. If you give a limit of the absolute value of x over x, x goes to 0 positive.
It would be positive 1.
Positive 1, very good. So this would be positive 1. Because x goes to 0 positive, you see, if this is going to be the case, again, same thing, you say, oh, x is positive. So, oh, absolute value of x is x. Okay, so, all the possibilities you have to consider, but you want any question? So what's the answer to this one? Limit of absolute value of x over x, x goes to 0.
Positive 1.
Why
B
positive?
does not exist.
Oh, yeah,
because
it does
they're
not
equal
exist.
to each
Yeah,
other.
Does not ex-
yeah.
yeah. You say if you don't have positive negative, you cannot decide. So you have to break it yourself. Okay, you break it yourself. So, oh, I want to find this one. So if you want to find this, you see the answer would be, you are going to break it in 2 parts. You say that the limit of the absolute value of x over x, x goes to 0 negative is a negative 1. and the limit of the absolute value of x over x goes to 0 positive, is positive 1. So, you know, the right and the left limits are not the same. So the conclusion is that that limit, okay, when x goes to 0, does not exist. So it's always the case with the absolute value. We give you one of them, one absolute value, don't squeeze. Because we
How
need
about
it.
approaching 1?
Yeah, 1, no problem. You substitute. You see, if you're approaching 1, you put the 1 on the top and the bottom would be 1, 1 is 1.
Oh, sorry, approaching 1 from the left. Because then it can either be 0.
Which one? Approaching 1?
Yeah, approaching
No,
1
no.
from the left.
It doesn't matter because the 1 is positive number. You see, the difficulty is the partition point for this part here, the absolute value of x. If you get x equal to 1, you are not going to have 0, 0. You just direct substitute. If x goes to 1, doesn't matter, 1 positive, 1 negative, whatever. The only number that you are going to be in trouble is 0. Nothing else, you see? Because the 0 can make you 0, 0. You see? If it's going to be anything else, there you are. If you have the limit of the absolute value of x over x goes to 1 positive. It doesn't matter. It's a 1, 1. Absolute value of 1, 1, 1. You see? Because the 0, 0 case is the one that you cannot say that. You know that when x goes to 1 positive means what? Means x is bigger than 1. X is positive. So for the absolute value case, the only time that you are going to be in trouble when we get the case of the 0, 0. Otherwise, you can find it. Limit of x goes to 5. It's 5, 5, 1. Okay, negative 5. Negative 5, then again, we get the negative 1. So these are going to be the case. The only difficulty is 0, 0. Okay, any question? So we want to give you now this idea of because there is a place that we are going to use these facts. So that's a type 2, if you like. Let's go to the type 3. The type 3 is going to be a radical one, remember? We have 2, 3 over here. Okay, so I did the part C on the lecture notes. Okay, so I'm not going to repeat it. This one is easy. We checked it before. Okay, so I'm not going to do this one. I do the number part D for you. We give you something like D or E. Okay, because you know the C is just a single radical. So this is similar to one of the problem in your book. And we want to be patient and don't expect to have a nice numbers all the time. It's okay, we can do it. You see, that's the limits that you want to find. Again, direct substitution. You see, all of them you substitute. When you substitute, you may get the answer. But if you get a 0, 0, then you have to apply these methods. So substitute. What's going to be the result if you direct substitute x equal to 1? So that gives you 2 plus 1 minus radical 3, and that would be 1 minus 1. So the top would be radical 3 minus radical 3, which is 0, 0. Okay, so what's the message for this one? 0, 0. Message. We know that there is a common factor. What is that common factor in this case?
X minus 1.
X minus 1, excellent. Say x goes to 1, so x minus 1 is a factor. So x minus 1 is a common factor. Common factor. So we have to find it and eliminate it. You see the bottom one, we already got x minus 1. The top is the radical expressions. We talk about it. When we get the radical expression, you have to multiply the top and the bottom by the conjugate of the radical expression. So we need a little bit algebra to continue. Okay, so we have to go back and start it over. Okay, so this is it. This is the original one. Have to repeat it. 2x plus 1 minus radical 3x minus 1 is going to be the same as limit. You multiply the top and the bottom by the conjugate of the top. You see the conjugate would be radical 2x plus 1. Just changing the middle sign, plus radical 3. That's for the top. The same thing down the bottom, 2x plus 1 radical 3. So this is a radical 2x plus 1 minus radical 3. And this is x minus 1. Okay, so I multiply the top and the bottom by the conjugate of the radical expression. Conjugate means you change this one into the positive. Now, x minus 1 is already here. So you're not going to do anything to the bottom. But you have to continue on the top, multiply it, especially for in method, to create x minus 1 on the top. Automatically you should get it. Otherwise you probably miss something. Okay, so multiply the top. Limit of x goes to 1. Remember a special FOIL method. You multiply these two together, a square of the first minus the square of a second. So it's going to be radical 2x plus 1 all squared minus radical 3 all squared. FOIL, a special FOIL. Don't do anything to the bottom. Keep it as is. So we just repeat it. You continue on the top to get x minus 1. So on the top, you square these, you remove the radicals. So this is going to be the case, the limit of x goes to 1. The top that give you 2x plus 1 minus 3. The bottom one again as is. Don't do anything to it. Plus radical 3 times x minus 1. Continue on the top. Remember, you are looking for x minus 1. So on the top, you combine the like terms. Plus 1 minus 3 would be negative 2. So that gives you the limit of x goes to 1. That's a 2x minus 2. And this is going to be radical 2x plus 1 plus radical 3 times it by x minus 1. We need x minus 1 on the top. What are we going to do to get it?
Factor out of 2.
Factor out the 2, very good. X goes to 1. 2 out, so that gives us x minus 1. And that's a radical 2x plus 1. Okay, plus radical 3 and the x minus 1. This is the time to eliminate. Remember, limit. You're not going to drop the limits because you're not done. Okay, to get this out. Okay, very good. Now divide out by x minus 1. So the leftover, see, we remove the common factor. So we are ready to find. That's it. It's a 2x plus 1 plus radical 3. Okay, you remove the common factor. Now direct substitution give you the result. Replace x by 1. So that give you 2. And that would be 2 plus 1 inside, radical 3. So that give you 2. This is going to be radical 3 plus radical 3. Don't use calculator or decimal numbers, anything. So that give you 2. Combine the radicals, 2 radical 3s. So the 2 and 2 cancel out, 1 over radical 3. You know, even we accept this one as the final answer, but we can rationalize it if you like. Okay, if you rationalize it, that gives radical 3 over 3. Either one is fine. You know, we accept both of them. All the time, you know, the numbers are nice, but I just want to give you something different so that, you know, don't worry. You see, it's going to be come out nicely. So this is a very important case, as I talked about the other day, and we give one of them to check, and because we are going to use it twice in future. Okay, so be careful, you know, combining the like terms over there, and to keep it in order, and you'll be fine. Okay, any question? So that's with the rational function. There is a part E is a similar, you can do it yourself. Okay, so I just give you the answer to that one too. So just check it. So that's a part C, D, and part E is this one. Okay, part E, you want to find the limit of, okay, it's a limit of x plus 7, okay, x plus 7 minus 3 divided by x minus 2, x equal to 2. Okay, you check it. You know, the same thing, you have to, it's going to be 0, 0 again. You find the common factor, you eliminate it, and the final answer is going to be 1, 6. Okay, it's going to be 1, 1, 6. Okay, I leave a space here when I post this one for you. I give you the solution here. Okay, but you can check it for yourself to just make sure you know it. Okay, so that's going to be the case for number E. And the case number F is the same thing. Okay, it's a piecewise defined function. So that's going to be the case E and the F. I just, when I post it, I give you the solution for F as well. Okay, it's like number 1 that we did. So that would be our case. Okay, so that's going to be 0, 0. We need one more of these cases. Let's see if we have it. Oh, we don't have one of those cases. I have to give you one myself. Okay, so we need one, you know that we need those rational types. So I give you one, EF. Any question? So the missing one is this one. Okay, the last one is IJ. You can call it K if you like. I'm going to call it 3K, but we need this example. It's missing. So we want to find this limit. The limit of, you see the case, it's a very important case that we're going to use in future quite a lot. So it's going to be 2x plus 1. Okay, 2x plus 1 on the top. And down the bottom, let's have x plus 4. I want to find the limit of, so let's say x goes to -1. Okay, so I put the x plus 1 over here for you. And on the top, it's going to be minus, I have to cheat. If I put the -3 here, -1, that give me -1 on the top. I think a 1/3 would do it for us. Okay. If I put the -1 here, so that give me -1 plus 1/3. Okay, you need these limits. You must know it. So I just add this one to the collection. I may revise that one and check it. Okay, remember this is the case that if you substitute, you get 0, 0, but on the top are just fractions. So the case 1 is polynomials on the top and the bottom. The case 2, rational functions on the top. Case 3, complex functions. So check solution. Check to see it's going to be 0, 0. So I just substitute directly to confirm it. So I put the -1 here, so that give me -2 plus 1. That give me -1 plus 4. And this is a plus 1/3. And over here, I get the -1 plus 1. So on the top, I have a -1 on the top, a +3 here, and the plus 1/3. As you can see, I have a 0, 0. That's it. Nice. Okay, what's the message for this one? You get the 0, 0.
X plus 1 is a common factor.
Excellent, that's it. You need a common factor. X goes to -1, so x plus 1 is a common factor. X plus 1 is a common factor. Okay, common factor. Now we're going to create it. Since it's a complex fraction on the top, we just add these two fractions. That's it. If you add them together, that x plus 1 would appear on the top. You eliminate it, then you're done. Okay, so that's case 3. So the case 1, polynomials on the top and the bottom, you factor it. Case 2, radicals on the top, you remove the radicals by multiplying by the conjugate. The case 3, complex functions. Okay, so let's do it. We go back and we just combine them together. So it's going to be the limit of x goes to -1. Carefully, just just add them like in algebra. You find the common denominator, which is going to be the product. 3 times x plus 4. And you divide. You see, you divide this one. You know that as like in algebra, you divide the new fraction by the denominator by the old one. The leftover is going to be 3 times the top. Plus, you do the same thing here. You divide the new denominator by the old one. The leftover is going to be x plus 1, x plus 4 times 1. I write it down so that you know what's going on. You see, it's like cross multiplication. You see, 3 times 2x plus 1 plus 1 times x plus 4. Any question? Move on the top. You cannot simplify it, so go on. Multiply, combine the like terms, you must get x plus 1. So we continue. It's going to be equal to the limit of, again, limit all the time. So that gives us x plus 1. Combine the like terms on the top, carefully multiply 3 inside, 6x plus 3. And that would be plus x plus 4. Okay, continue on the top. Combine the like terms, you must get that common factor. X goes to -1. The top 6x and x would be 7x. 3 and 4 would be 7. Okay, sorry, I have to get this one up a little bit. So I have a 7x plus 7. The numerator stay the same, 3 times x plus 4. Then divide by x plus 1. Remember, you need x plus 1 on the top. This is 7x plus 7, factor out the 7. So that gives a limit of x goes to -1. That's it, 3 times x plus 4. 7 out. That gives us x plus 1, and that's going to be x plus 1. Now x plus 1 and x plus 1 would cancel out. So this is going to be 1. So the leftover on the top is simply x goes to -1. You get 7 over 3 times x plus 4. Now you substitute. You substitute -1, so that gives us 7. And that would be 3 times -1 plus 4. So this is going to be 7 over 3 times 3, which is 7, 9. So the 7, 9 is going to be the final answer. Okay, it's very nice case, and it's going to be used, okay, in future. That's why I was surprised that I didn't have it over here. So that's why I added it, so that we can have it nicely. Okay, so this is 3 famous cases for these numbers. So that would be case 3. You have more here, G, H, I, J, they are all the same. I will add it, and then when I post the solution for you, then you will see it. I put it in these lecture notes, okay? So You can check it for yourself, but you will see it. Okay. So that's going to be the case for number 3. Any question? So that give you the idea that what type of problems we are going to be interested in, even for the rest of the course, really. And these are going to be the challenging one. Okay, so the other parts are easy. These are going to be the G. I leave this space. I will put those solution for you. Then I will post this. Okay. So that's the case. The other case is using the squeeze theorem. Okay. So it's going to be one of these limits. It's not going to be a separate question. And it's not going to be expressed like number 4. Then they say use the squeeze theorem. We want you to yourself, okay, to recognize it, that you have to use the squeeze theorem to get these numbers. Okay. So this is how we are going to do it. That's a number 4. Okay, number 4, we want to find each limits. So we are going to give only find the limit. Find the limit. Okay, I'll just give you explain the 2 of these. Part B is this one, limit of x squared sine of. You can make it as complicated. I picked this one because this is, I think, one of the problem in your book. X goes to 0. You see, these problems can be done only by a squeeze theorem. So this means you have to squeeze this one into between 2 other functions. You know that. You need a kind of inequality, and then you take the limits. We already talked about how we're going to make this inequality for these. You cannot use it by substitution, because if you put x equal to the 0, that gives you the 0. And some people, they say, oh, that's enough for the limit to be 0, but it's not. Because the second one, if you put the 0, you see the sign of the whatever it is over x is that limit does not exist. So you cannot use the, okay, you cannot use the product rule. So we start making inequality. This we may be sine or cosine. Whichever is given to you is between 1 and -1. So this is how you start with this type of function. Note that. You set the sign of whatever. It doesn't matter what is inside, really. In this case, is a 50 pi cube root of x. Is always between 1 and negative. You see, either sine or cosine, whatever it is given to you. It's always between -1 and 1. The only restriction is the x is down the denominator, so you have to assume that the x is not equal to the 0. It's not a big deal because x goes to 0, so x is not equal to the 0. Okay, so if it is cosine, you start with the cosine between -1 and 1. If it's a sine, you start with the sine. Now create whatever you like, you want. You want x squared times it by x squared. If you need x to the 5th, multiply by x to the 5th. So times it by x squared, okay, multiply by whatever you need, by x squared. So this makes it into the negative x squared sine of 50 pi over cube root of x less than equal to the x squared, you see? So you squeeze your function between 2 other functions. That's why we call it a squeezing theorem. Now what's going to be next step? You find the limit of the function to the left, the function to the right. At what? At x goes to 0. If they happen to be the same, that same numbers is the limit of the middle one. Very easy question. You find the limit here. Limit of negative x squared, x goes to 0. Whatever it is, 0 positive, 0 negative, that gives you 0. You do the same thing here. The limit of x squared, x goes to 0 is 0. Since you get these two, the conclusion is going to be by a squeeze theorem, SQ, the squeeze theorem. The limit of the middle one, x squared sine of 50 pi over cube root of x, okay, when x is also equal to the 0 and you're done. Okay, so it's very, very easy question. But some people, they made a mess over here when they explain it. We need, you see, you need this inequality. Without this inequality, you can't do it. But the order that you create this inequality is important. You see, the order is start with the sine or cosine, whichever is given to you. Sine between -1 and 1. Cosine between -1 and 1. Then multiply by whatever you have. If you have x squared, you multiply by x squared. If you have the x, you multiply by x. Automatically, you create your inequality. Then the limit part is easy. You find the limit of the function to the right, to the left. If they happen to be the same, that same number is going to be your limit. It's always the same. Okay, so it's not going to be a big deal for this problem. Any question? So this would be part of those 4 limits that you're going to find for us. So that gives us a number 4. You don't have to spend more time on this one. And that takes us to the last one that we did today, continuity. So that's the 4th question on the limits. I repeat it again, you see, as I did, and you will see them right tomorrow. So the first topic, piecewise defined function. Right, left limit, exact value of the function, and its converse. Converse means finding the m so that the right and the left limits are going to be the same. That's first one. Second one, special limits. Special limits, we break it into 3 different problems. So we get the case 0, 0 when we get the polynomials. We case the z0 when we get the absolute value. We get the case 0, 0 when we get the radical function. Those conjugate that we talk about it. You case the case 0, 0 when we get the rational functions. Okay, so that will, and the squeeze theorem, that will give you what? That give you 3 problems, 2 parts each, 6 limits to find. So that make it to the 3 question on the, okay, 4 questions on the limit parts. So the rest continuity that I'm going to check for you. Any question? What's the question? Only work with the, yes, sine and the cosine are popular for the squeeze theorem because the inequality is easy to find. And the reason that they give you this one, because the other part, you see, they have to give you the inequality. That's the case. They, you know, you cannot have it for the, you may have it for the tangent or anything else, but we go with the sine and the cosine because it's easy for us to find the inequality at this level. Otherwise, they have to give you the inequality. Yes, it's going to be sine and cosine. Okay, let's check this continuity one. 2 questions of continuity, whatever I did today. There are 4 groups of functions, okay? We give it 2 questions and we put all these functions on those 2 questions. It's like finding the domain of the function, except the piecewise defined value, okay? Are you ready? Number 5. We did it today, it's just a repetition of those. We want to determine where each function is continuous. Where means intervals only, okay? We like the interval notations. Remember, we talked about, we give you the theorem was polynomials are continuous, and it's just using this one again and again and again. First one, you identify the type of the function and you give us the answer. That's it. X cubed minus 2x plus 3. That's it. First one. What type of function is this one?
Polynomial.
Where this is continuous
Everywhere.
and sit, done, solution. You have to mention that it's a polynomial. F is a polynomial. It's going to be repeated over and over in this course. And is continuous on the negative infinity, positive infinity. Done. Okay, we don't make it complicated. You don't need it. That's great. Weierstrass theorem. Because remember, the continuity means the limit and the exact value are the same. It's a polynomial. We always get the direct substitution to get it done. That's case one. Any question? Case two. Gx top 3x plus 1. Oh, this is the one that I have to change it a little bit. Okay, and this is it. It's going to be x squared plus 7x. And suppose there is a misprint here. I can go with the original one. This is in fact from your book. But you get involved with the radicals. So we just change it to the no harm. I change it to the, see, original one is x squared plus 7x minus 2. I change it to the positive 12. That would be better. Suppose that's a misprint. Okay, rational function. Remember, the top is polynomial continue. The bottom one continuous. So what is the difficulty? The catch is you have to remove the zeros of the denominator. So factor it to find the wholes, if you like. G of x, 3x plus 1. So to factor it, what we need? You need two numbers with a product of 12 and a sum of 7. Numbers, any suggestion?
3 and 4.
3 and 4 or 4 and 3. That's it. There you are. So the number is going to be 0 at what? You see, the number would be 0 at -4 and -3. So you have to exclude the -4 and the -3. That's it. Okay, so this function is continuous everywhere except when we get x equal to -4 and we get a -3. Because the number would be 0, it's undefined. That's it. So, but write on interval notation. G is continuous. G is going to be continuous on this interval. -infinity to -4. Union with -4 and -3. Union with -3 and positive infinity, and you're done. Any question? So it's like finding the domain of the function really for this group. And nothing to worry about. Various part, they're all the same. We give you one of these rational functions only. Let's see what's special about this one, h of x. This is the one that some people, they missed it. You see. Again, it's a rational function. You have to factor the denominator first. Solution. H of x equal to x minus 4. X minus 4 times x plus 4. The point about this one is don't simplify it. Don't simplify it because you're just checking the continuity. Again, the number is going to be 0 at 2 places. So you have to exclude it. You see, you have to exclude the -4 and a +4 because of the denominator. So again, we get 2 wholes here. So the function is continuous everywhere except at -4. The reason that I gave you because I've seen some people, they simplify it. Then they say the function is continuous everywhere except at -4, which is not correct. 2 points. Okay, so don't miss it. H is continuous on its domain. On what? From negative infinity to negative 4. Make sure you use parentheses. Negative 4, 4, 4 and positive infinity. That's it. Any question?
Yeah, I have a question.
Yes.
What happens in a scenario where the denominator is non-factorable?
Yeah, we have it. We have one case. The next one.
Okay.
The next one is you see. Very good. Yeah. You see this one? So the number is not factorable. When it's not factorable, you won't get any hole here. So the function will be continuous forever. You see difficulty because each factor give you one number that you have to take out. When it's non-factorable, it means you can't have that number. So you can't have this continuity, okay? So this is how we explain, we say x squared plus 9. Okay, it's not factorable. Not factorable. And that's it. And so it's not 0. So that the number line is nice, you see, no holes. So your function is continuous everywhere. F is continuous. Okay, on all real numbers everywhere. So these are going to be various cases that we have. Any question? So study carefully. Yes, question.
Oh, sorry. On the test, do we have to write that x squared plus 9 is not factorable as the reason in
Of
our answer?
course,
Or can we just... Okay.
Yeah, you have to give us a reason, yeah. Okay, so case with the radicals, let's check the case with the radical too, then we have all the collections. And we put them together, as I talk about it, as one question or two questions. So let's check part E, which is one of those special ones that we have. What is the g of x? Is the square root of 9 minus x squared, radical function. You know that the inside is a polynomial, it's continuous. The difficulty is index of the radical. Index of this radical 2 is even. Since it's even, there is a restriction. You have to force the inside to be a non-negative, cannot be negative, okay? So this is the case that you have to work a little bit. So we say, oh, index of the radical 2 is even. Work to do. What work to do is, you have to check, say, this 3 or 4 information, g of x is continuous. Is going to be continuous when 9 minus x squared is greater than or equal to the 0. You see, this is where you have to your work to get this true. Remember the way we did it. Different way to solve this. My way is I move the 9 to the other side. Then I multiply by -1 both sides. To switch it. Okay, I multiply by -1. Then I have to switch the sign of the inequality or reverse it. Take the square root. Absolute value less than 3. Okay, number line. Negative infinity to positive infinity. Ohm, 0. 3 to the right, 3 to the left. You see, it's less. X less than 3, less you go inside. Greater than you go to the right, to the left. So the function is continuous on this interval. -3 and +3. You see the domain would be closed interval of -3 and 3. That's it. So G is continuous. G is continuous. Okay, on this domain, -3 and 3. And you're done. Okay, it depends if it's going to be greater than, as I did it during the lecture notes. Okay, the previous one, we just the portion to the right and to the left. But for this one, it's going to be the number inside right away. Okay, any question? And the last one that I have time to do for you is when the radical, the index is odd. Piecewise defined is like the one that I did, and check it yourself. So part F, this is the function. H of x is equal to cube root of x cubed minus 3x plus 7. That's the easiest one. Index is odd. Forget about radical. Inside is a polynomial. It's continuous forever. Okay, so that would be the easiest case. So the index 3 is odd. So h is continuous forever. Is continuous because it's a polynomial on R. D equal to negative infinity and positive infinity. And then you're done. Okay, so this is going to be number 6 are piecewise defined. This is where you have to check the partition point. Okay, I will add one of them when I do this, when I post the lecture notes, then you check it for yourself. I have my calculus 3 in 5 minutes. I have to go. And so that gives you the idea. And that's going to be your work for the first week. So we are done with the section 1.4. I think that's 1.5 are going to be infinite limits. Is not going to be important for the time being, but we are going to check it for you. Just give you 1 or 2 examples. So otherwise, we are done with whatever we need to know for this chapter. And very important one, this review that I did, and these problems are going to be your tools from now on.